and welcome everyone. As Lisa just told you, this is the electrical and computer engineering session, so I welcome you here on campus on behalf of our department. My name is Volker Nock. I'm one of the lecturers in the department. Can you guys in the back hear me all right? Yeah? So I'm German, I'm naturally loud, so I apologize for the dialect. I'll try and make it as understandable as possible. So what we're trying to do today is trying to give you an idea what a typical lecture is like. This is obviously not going to be a typical lecture. I'm not going to ask you to do any exams or tests afterwards, so you can relax. But just to give you a feeling what it's like to be a student in engineering or at Canterbury. So the topic I've chosen today is just to give you a bit of an introduction in why electrical and computer engineering is actually quite important. I know lots of you will interact with electricity daily and don't think about it. That's a good thing. That means engineering works. If you don't worry about it, if you don't are annoyed with something not working, that's what we want as engineers. We want to make daily life of people easier, better, healthier, more sustainable. You know, all of you get up in the morning, you press the button and the light comes on. Does anyone ever wonder why, how it does that? No, no one ever does, because it mostly works. The times when it doesn't work is when you start wondering what is actually going on. How does the electricity get to the city? How is the electricity generated? What can I do if there's no electricity? Challenge you guys to do a few days without electricity. It's actually quite tricky these days. So yeah, just a funny picture. Every one of you probably has one of these. I've got one of these. You'd be surprised how similar these phones are to us. A lot of the things that are inside this phone that you use on a daily basis are things that are inside your body already. Nature's got, or has had millions of years, billions of years to perfect the different sensors and different actuators that we have in our body. And we're trying to replicate it in things like smartphones. And you'll be surprised that your body actually runs on very similar physical principles. So your body runs on a lot of electricity. We don't usually realize that unless our body gets charged up and we zap each other when we touch each other or when we get out of the car. But basically your brain and everything else uses electricity to measure things, process data, and actually even to talk. So when I talk to you, some form of electricity has gone on in my head and has made my brain produce some words. And then I've got an actuator, which is my mouth, to actually produce the sound. So I'll just show you a few examples of where you can say this is exactly what is in the phone and this is what is in the body, just to give you a bit of a motivation why knowing about electricity is actually quite important. So as I said, so normally when I start my lectures, I introduce myself. So we usually have, we lecture about a term that's several weeks. So you see the students the first time, I introduce myself. So I'm a lecturer in electrical and computer engineering. If you want to come and see me, I'm in room 433 in the von Haas building, so my door is always open. Come and ask questions. Write me an email if you want to know more about the things I talk about here. My background is in micro and nanotechnology, so electrical engineering encompasses a lot of things. Obviously power, how to generate electricity, but also things like how do we build computers, microelectronics, how do we build robots, how do I get my scooter to be electrical. But yeah, at this really small end, we're doing what we call micro and nanotechnology. So we're trying to reduce the size of sensors. You all think about when you turn your mobile phone to the side, it knows exactly if it's upright or not. So there's a tiny little sensor in there that tells the phone, is it upright or not? When your car crashes into someone else's car, there's a little sensor that tells it that, and that inflates the airbag. So there's lots of these tiny little sensors that we make using micro and nanotechnology. Micro really means 10 to the minus 6 meters. Nano means 10 to the minus 9 meters. It's just a size scale. It's nothing else. But there's a lot of technology, and usually you need some quite fancy and clean equipment and facilities to make these devices. I'll show you an example of what we do here at Canterbury. We have one of these labs here. So just to get you started, so I'm asking you this question. What do you think, or what you and your cell phone have in common? You don't usually think that you do have a lot in common with a black box like this. I certainly can't sing as well as my phone can sing, but you'll be surprised. So much more than you would ever think. And I hope after this lecture I can I've convinced you a little bit that you're actually very similar to your smartphone. The most basic thing is that both of them depend almost entirely on the electric force to make things work inside the phone as well as inside your body. And you use electric currents to make things happen. So if your phone vibrates, it's because the battery has applied an electric current to a little motor that then vibrates the whole phone. If my brain wants my body to move, it tells via electrical and chemical signals my muscles to move. So same thing, uses electric currents. So yeah, it's definitely worth looking at electrical engineering because most things are driven by it. So yeah, you take a modern smartphone. What inside that smartphone is actually very similar to what's inside you or any human being. So say things like your smartphone has a camera, and these are quite amazing cameras these days. We used to have a camera just this size, would do nothing else but take pictures. Now we have a phone that has a tiny little camera attached to it. But what that camera does is basically converts light that comes in via a microelectronic sensor into electrical signals that then turn up as a picture on your screen. What would do the same thing in your body? It's a pretty simple question. It's your eyes. Yeah. So your eyes do exactly the same thing. Light hits your eyes. There are a few sensors in the back of your eyes that turn that into some form of electrical information, and that gets transmitted to your brain. And your brain is the little processor that you have in here as well, that then turns it into an image. So we've got one thing, we've got a light sensor. We're so used to it. I mean, you know what happens when you turn blind, it's pretty desperate. If you grow up without sight, people can get used to moving without sight, but if I close my eyes now, I'm going to be in trouble. I don't know where I'm going. So we're quite reliant on that. And it's all being done using electricity. So that was an easy one. Sound, we see that's another easy one. Your phones will have some form of little microphone, usually at the bottom. Some of them have two, so you can hold it in both directions. Again, it will be a very tiny little component that converts, in this case, pressure or changes in pressure. So when I speak, my mouth generates pressure waves and they come to your ear. Gave it away. So in the human body would be the ear. So your ear would translate that pressure wave into an electrical signal that then goes into your brain and gets turned into words. You're starting to realize the brain is quite important. The brain does all the processing. But yeah, if you look at it, what we have in these devices is we basically have these tiny little membranes that we can make now. They're thinner than a human hair. And we can put little pressure sensors on top of these, so when the membranes vibrate, they turn that into an electrical signal. And that's very similar in a way to what your ear does. In your ear, you have some very small mechanical components, little bones, that vibrate according to the frequency of the sound that I'm talking to you or the music that you hear. So if you look at your ear, you can zoom in. There's some really fascinating little structures in there that have just developed. So no one has designed these. They've just developed to a precise way. Whereas we're still spending quite basic technology on this. We're still not very anywhere close to what your body can do. But we're certainly copying a lot of things that your body does. So that's something you come across in engineering a lot, is what we call biomimetics. So we look at what nature does, we look at what animals do, we look at what humans do, and we try and produce artificial systems, be them mechanical, electrical or not, that do a similar thing. So we don't have to always invent everything new. Quite often we can just copy. We're quite good at copying things from nature. Okay, so you're all used to the fact that, yeah, depending which way you turn your phone, the screen will turn. So something in the phone will need to be able to tell which direction it's facing, what angle it's at. And that's very similar to the devices that we use to measure whether a car has crashed into another car. We call these accelerometers. So they measure acceleration with certain axes. So you can measure in, usually you've got 3 sensors, one for each direction, and you can tell which angle the phone is at. Do you want to guess what in your body does that? So I can stand up straight. There's people that can't do that because their feeling of balance is not very good. Does anyone know which organ in the body does? Yep. So the ear turns out, does not just do sound, it also does balance. So if you have problems, if you have a tinnitus or something, you've got sensitive ears, people get very sensitive to being off balance as well. So whereas these sensors here that we make are very complex little mechanical vibrators, and as soon as you tilt them, they vibrate at different frequencies. In the ear, you have very similar little mechanical vibration devices. So you can get yourself quite lost when you lose that ability. It'd be surprising how you're used to being able to know if you're standing upright or not. But if you don't have that feeling anymore, it is really awkward. Your phones obviously can detect force as well. You're all using the touch screen to input data, to write, to draw. And what it does, it's on the surface of the screen, it has, again, a film that's sensitive to how hard you press. The early screens would just measure, do I press or not? So it can just detect whether your finger is there or not. The newer screens can actually detect how hard you press. So you might have heard that there was in the news recently where Android phones weren't able to do that yet, and Apple was saying, well, our phones can do that. But it turns out all these screens can measure force. So depending on how hard you press, you can actually say, I want the screen to do something completely different than when I just briefly touch it. The way we do this in the screens is that we apply an electric field to the backside of the screen, and as soon as you put your finger close to it, it distorts that electric field. It's not very strong, you don't feel it, you don't get zapped when you touch the screen. But what you're actually doing there, because your body is conductive, you've got water in your body, it will actually change the electric field lines, and we can detect that. So through another electrode, we can say there was a finger in between those two electrodes. So that should turn into an E or an A or something else. Does anyone want to guess what in the human body does force detection? Skin. So if you run into an obstacle, you can tell that there's an obstacle. And the first thing that touches the obstacle is your skin. So if you touch something, you can feel that there is something there. So in our human body, or in animals as well, the skin actually has pressure transducers on the backside. So you will be able to tell. And again, there's certain diseases where people can't tell that there's an obstacle. It's quite important to find out, what's going wrong there. But what happens with the skin is, again, the sensors or the skin turns that into an electrical chemical signal that goes to your brain. And your brain goes like, oops, wait a minute, there's a table in front of you, or at least something solid. You can't go any further, so it tells your muscles to stop. You do that automatically, you don't think about it. But again, it's an electrical signal that comes from your skin and goes to your brain and gets processed and tells you to stop. You all know that your battery in your phone is never big enough, so you have to have some form of energy source. So that's not really a sensor, but that's what keeps you going in the phone. And there's certainly a lot to be improved in these phones. You get about a day or 2 days worth of use out of it. You think about how long you can operate your body without putting any extra energy in. It's not that dissimilar. And you certainly get really hungry after 2 days. But yeah, think about what in your human body would be equivalent to the battery. And it turns out you have that whole digestive system that does that. So that turns food, which is basically chemicals, into useful materials that you can then in your body turn into energy, which quite often is electricity as well. So your body doesn't run completely on electricity, but some of the chemical reactions that are going on actually do generate the electricity that your nerve cells use and your brain uses as well. So again, very similar to the phone, there's something in your body that is an energy source or an energy storage device. If you have a full stomach, that's equivalent to having a full battery. On these phones, if you've ever opened one up, and I don't always recommend that, but certainly if you have an old one, it's really worth opening it up and seeing what's inside. It's not just a black box, there's actually a lot of things in there. You usually have a plastic board that has all these little connections on it. So you've got a central processor, you've got your camera, you've got other things. They need to be connected. What we use in electrical engineering are printed circuit boards. So they've got conductive traces on the surface that connect the different parts. And again, in your body, you have to have something that connects your senses, like your eyes to the brain, your leg muscles to the brain. So you have to have something that provides control and connectivity. And again, that shouldn't be a difficult question. You already probably talked about this in biology, but you've got your nerve system. And your nerves actually run to a large degree on electricity. So you've got these tiny little wires that go through your whole body, all of them, or most of them, ending up in the brain. So that's very similar to these wires ending up in the processor. Processor being your brain. So if down here, and if something is detected, it travels all the way up to the spinal cord and then all the way up into the brain. And then the brain says, well, need to do something. So it sends a signal back along the nerve system, and that tells your muscles to make a fist or whatever else is appropriate in that case. So you've got a whole electrical control system inside your body. Now, I've mentioned this already. Your phone has one central piece of electrical circuit, an integrated circuit, that controls it, that does all the processing. You could call it a brain. It's usually only as smart as the person that has programmed it. But it takes all the input from all the sensors, your cameras, your light sensors, your touch screen. You could have anything on that phone, and it turns it into something useful that we can understand. Human body, it's the brain. So we're so used to the fact that if we just look at something, it makes sense. I look at this door and it is a door. I've got that knowledge, stored data in my brain that tells me, well, something that looks about that shape and that size should be a door. It's not obvious. You have to learn all that. And the processors have to learn that as well. So if you think about, if you have heard the term machine learning, a lot of these approaches are that we try to get the robots to do things by themselves. They can't do that unless we teach them how to do it. Because they don't have the years that you've spent as kids trying to open doors and learning along the way. We actually need to teach the robots that as well. And they need to store that information in some way. So the brain or the processor in that way are very important components. If you look at some of the newer devices at the moment, they have about 2 billion transistors. So transistors are little switches that switch on and off electrical signals. I think NVIDIA a week ago came out with a new graphics chip that has about 15 billion transistors on it. Those transistors are roughly 100,000 times smaller than a human hair. And we can make 15 billion of them working in tandem. The thing is, if you look at the brain, we're just not there yet. You have about 100 billion, depends who you talk to. Depends how old you are, whether you're human or not. But roughly 100 billion neurons in your brain. So we're about 10 times away from what we can build in terms of just plain switching capability that the brain has compared to the processes that we can make. So there's plenty of work for you guys. And it's certainly a very interesting field to be in terms of developing these devices. The smallest building blocks, as I said, is currently what we call these FinFET transistors. So they've got a little fin. The current can go through here, and by applying a voltage to the gate, you can switch it on or off. It's like squeezing a hose. Either you let the water come through or not. And that's the smallest building block that we use in electrical engineering. They're tiny. They're about 10 nanometers at the moment. So very close to the limit of what we can do with single atoms. And in the human body, it's slightly larger, but if you want to put an equivalent in, it would be something like a neuron. There's obviously a lot more chemistry going on there. It's not just electrical engineering, it's converting molecules, and these molecules have charges. So it's a little bit more complex, but the basic building block in the brain would be the neuron, and the smartphone would be the transistor. What have these two in common? Well, I hope you have sort of picked up where I'm getting at. Both of these depend almost entirely on the electric force and use electric currents to make things happen. So you're actually very similar to your smartphone in the way you operate. The cool thing is that transistors as well as neurons can be described in electrical engineering by some very fundamental equations, just 4 of them really. You could drill everything down to these 4 equations that you might have heard in physics, Maxwell's equations. It was James Clerk Maxwell discovered those in the 1800s. And it turns out you can describe neurons as well as transistors with these. You can describe anything. So we have got some very simplified equations. They might seem weird when you hear about them the first time, but if you realize that pretty much everything in that area you can describe using these equations, it's pretty beautiful. I'm not going to bore you with these equations. I'm going to show you in the end just a few things that we do in electrical engineering. So you don't just use electric force to make phones or your body operate, but you learn quite a lot of interesting things when you study engineering. So what we have here at Canterbury is what we call a high voltage lab. So you learn all about how is power generated, how is it transferred from the power station to the cities, how do we use it when it gets to the cities. There's an example where the students build what we call Tesla coil. So you've got a little high voltage arc here that you can modulate music onto it. So there's no loudspeaker, it's just the vibration of that high voltage arc that does that. So you learn how to build things like that. Might not be very useful, but it's certainly a really cool application of what Tesla discovered back in the days. The other thing that you might not think about when you talk about electrical engineering is that we do things like rockets. So we've got a big research group that looks at how to control rockets. So we're not making electrical rockets, but we're making the control systems of the rockets. So Chris Hahn's group, they regularly go out and launch rockets out in Birdlings Flat. They're some of the world's best control systems that they generate. So these rockets, they can control the path of these no matter how chaotic the wind is around them. And for that, they need very fast microprocessors, and then they can steer them and control where they're going. So they're very close to launching one up to several kilometers soon. And you might have heard of Rocket Lab in Auckland. They're actually building commercial rockets now in New Zealand, and they're going to launch satellites from here. So that's something you might not think about when you think about electrical engineering. The other things you can learn here are, for example, how to make solar cells. So you might all be aware that we're in trouble with oil. Oil is going to run out at some stage. So as one of the courses that we do here, you actually get to make your own solar cells. So you start with a silicon wafer, which is a piece of ultra pure sand, same material that we make the microprocessors on, and you actually learn and make these cells yourself. At the same time, we teach you things like how you can make, for example, flexible solar cells. So while these ones are quite nice, they get really high efficiency, they're quite difficult to put on roofs. But if you can make something like this, and this is a solar cell as well, you can actually coat surfaces of buildings, roofs, everything, and generate renewable electricity. So those are the sort of things we do in nanotechnology. Or something very popular, obviously, is robots. So a robot certainly is a little bit of mechanical system as well. But what makes it smart are the electronics, are the sensors, the microprocessors, all the things that do the power sensor conversion. So this is an example of a course where the students actually get to build these individual little robots. We call them wacky races, and as one part of their exam, they actually race the robots against each other on an obstacle course. So they have to either control them by remote control, or the robots have to go completely autonomous. In this case, they're also allowed to impede the other robots. They can put contraptions on their robots and try and destroy the other robots if they want to. So it's a lot of fun. To give you an idea what you end up working in, just in the end, some of the projects that our students then work on, they usually work on with companies. So the final year projects tend to be about a year long in your final year. And you get to work on real commercial examples. So we've had students working with Trimble, a company here in Christchurch. They're putting UAVs on their diggers so that you can have a view of the construction site. You have that UAV not just flying free, but you have to attach it with a wire so that it can fly indefinitely. It doesn't need charging. So the students are just developing those systems. We've had students working with dynamic control So people in wheelchairs, they can actually control them using their smartphones now. So you can drive the wheelchair around. If you're in the bed and you want the chair to come to yourself, you just use the phone to get it to come to you. You obviously have to think about security. You don't want someone else to hijack your wheelchair, so you have to think about computer security as well. You're working on X-ray, colored X-ray, so you can tell the difference between different materials. Or you can figure out where firemen are in buildings. That's not a trivial problem either. So Tate Electronics, our students have worked on systems where they can actually determine where the firefighter is in the building. So you can see if they're still alive or not. So very, very interesting, very practical problems. So if you want to find out more, come to our department, come to our website, have a look. We certainly love to see you again. Good money to be earned in electrical engineering, and it's a lot of fun as well. So I recommend you have a look at some of these, do some recommended reading. So thank you.